Eulerian description and the other is the Lagrangian description. So in the Eulerian description, we we measure all quantities at a certain position. So then the quantities like density, pressure, velocity are specified as a function of position and of time. So we allow the fluid to flow through that point, but at any instant of time, we measure the value of various quantities at that point. The other is the Lagrangian, where you take your measurements following an element of fluid. But more commonly, we use the Eulerian description. So then the question comes, at any instant of time, if I'm given the velocity distribution, if I'm calculating it, so I have a certain flow situation and I want to calculate what is the velocity, what is the pressure, etc. Now, the fluid must satisfy the physical conservation laws. So the total amount of fluid must remain conserved. The rate of change of momentum must be proportional to force. So these laws must be satisfied. So if I have a field, velocity field and a pressure field and a density field specified in Eulerian description, how do I guarantee that these conservation laws are satisfied? Because if I'm simulating it, if I'm calculating it theoretically, so when I say theoretically, it could be either an analytical solution or a numerical solution. For the solution to be a valid physical solution, it is essential that the conservation laws, conservation of mass, and the momentum equation must be satisfied. So how do we guarantee it? So let's come to this the simplest of the conservation laws. The conservation of mass. This leads to so if we require that mass should be conserved, then it will lead to the continuity equation. So how do we impose conservation of mass and how does it lead to the continuity equation? So we have to start from the Reynolds transport theorem. The Reynolds transport theorem says so just recapitulating what this represents, B is a physical quantity, an extensive quantity, and beta is the corresponding intensive quantity, which means beta is B per unit mass. So then if I consider a system, when I say system, it means certain amount of material. So it encloses a certain mass of material. So if I follow a certain mass of material as it moves with time, then the rate of change of property B for that total system, if I correlate with the control volume approach, then the system, if you remember, the system boundary moves. So material moves in, moves out of the control volume as you follow the system. So the rate of change of B for the system is the rate of change of B inside the control volume. So if I integrate beta into the mass of the element and integrate over the control volume, this is B in the entire control volume. So the rate of change of B of the system is the rate of change in the control volume plus the rate at which it moves out. So if it is an uniformly expanding system, so the system boundary will expand. So let's say we have no inlet, where it's only expanding outwards. So let's say I have a control volume like this, and I have outward velocity everywhere. Then the system boundary moves out with time. So the rate of change in the entire system, so which means the expanding volume, is the rate of change inside the control volume plus the rate at which it goes out. And then we had shown that if we have mass flowing in, then also this is valid. So now let's consider a particular physical property. Let us say B is equal to mass, the mass of the system. Then beta, which is mass per unit mass, would be 1. Now, the system by definition encloses a certain amount of material. Material doesn't flow in or flow out of the system. So the system by definition follows the material as it moves with time. So then, ignoring the possibility of conversion of mass to energy, which is negligible usually in mechanical systems. So then the mass of the system must remain constant. So the rate of change of mass of the system must be 0. Now using the Reynolds transport theorem, I can write it the dm system rate of change in the control volume, which is beta rho dv. Beta is 1, so this is simply this, plus beta into beta rho v dot dA. So beta is 1, so it is rho v dot dA. And since dm system by dt is 0, this must be equal to 0. Now, if I consider a velocity field in the Eulerian description, and let me concentrate on a small element. So to start with, to make our work easy, let us say we have a system described by Cartesian coordinates. In this coordinate system, let me choose a small element, a rectangular element with dimensions dx, dy, and dz in x, y, and z directions. So then this is dx, this is dy, and dz. Now, if I evaluate all these terms, where what it gives me would guarantee that mass of the system is conserved. So if it's a small element, so in general, rho would have a Taylor expansion around the center point, but then the remaining terms, so to leading order, I would have rho. So let's say my x, y, z is at the center point of this rectangle. Let's say my x, y, z is at the center point of this rectangle. In that case, as I move away from the center point, the value of rho would change. It would be governed by the Taylor expansion in x, y, and z. But the corrections would be higher order in dx, dy, and dz. So the next order terms would be del rho by del x into dx. So in general, you would have an expansion like this, where xyz is the coordinate of the center, plus and higher order terms. Now, if you substitute this here and then carry out the integration, the contribution, if the element is infinitesimally small, the contribution from these terms would be one order smaller than this. So in the limit dx, dy, dz tending to 0, these can be dropped. So only this can be retained. So for an infinitesimal element, I can use this approximation. So the first term in this equation, del by del t of this integral we know. Now in the Eulerian description, everything is specified as function of position and time. So our independent variables are x, y, z and t if we use a Cartesian coordinate system. So therefore x, y, z are independent of t. So if I take the differentiation with respect to t, this will give me so that takes care of this term. Now we have to evaluate this. So let us look at the various parts of the control surface. So let me consider the 6 faces of this rectangular parallelepiped in sets of 2, the 2 which are parallel to each other. So areas are normally specified by the area is a vector specified, the direction of that vector is in the direction of the normal. So let me first, going in sequence x, y, z, let me first consider the areas which are perpendicular to x. So this is one and this is the other. So I use the shorthand term x faces to mean the faces which have their normal in the x direction. So if my xyz is the center point, then this face is at x plus dx by 2 and this face is at x minus dx by 2. So this is at x minus dx by 2 and this is at x plus dx by 2. So then the contribution from the uh, x plus dx by 2, if I see, I have to evaluate v dot dA. Now dA is a vector which points in the outward direction. So if you remember when we derived the Reynolds transport theorem, that was the convention we used, that on the control surface, the vector A always has the direction of the outward normal. So if I see the outward normal for this control volume, at x plus dx by 2, it is in the x direction. So if it's in the x direction, the Vx by definition is in the positive, the value of the component of V in the positive x direction. So for this phase, dA is also in the positive direction. So if I see the so we would have okay. Just one small question. Um, the unit vectors, what notation are you used to? The commonly used notation, one is ijk and the other is ex, ey, ez. Now, which of these do you normally use?
Sir, IJK.
Okay, then I'll stick to ijk. So V I can represent in this form, and on the x plus dx by 2 phase, the area, the magnitude is, so this was dx, this is dy, this is dz. So the magnitude is dy into dz, because this was dx, this is dy, and this is dz. So this face has area dy into dz, and the x plus dx by 2, the area, the normal vector is in the x direction. So the vector dA is this. So I dot j is 0, I dot k is 0. So this becomes Vx dy dz. On the x minus dx by 2 phase, V dot dA would be dot dot because the x minus dx by 2, that has an outward normal in this direction, which is the minus x direction. So the direction is minus I. So then this would be minus Vx So let me put this in parentheses. So the contribution to the surface integral from the two faces. So the contribution to the surface integral from the two faces would be so once again, in computing the surface integral over an infinitesimal area, I am neglecting the variation of rho or v with y or z, because those will be higher order terms. So then I am representing this as so on the x plus x by 2. So I am considering now the contribution to the surface integral from the two x spaces. So on the x plus dx by 2, I take the value of this quantity. So rho Vx at x plus dx by 2 into dy into dz. And for the contribution from this, rho v dot dA would be minus rho vx dy dz. So in evaluating the contribution to this integral from the two x faces, I take into account the sign of the v dot dA, and then for this surface, I have to take the values of rho and v at x plus dx by 2, and at this surface, I have to take the value at x minus dx by 2. So then I can tailor expand these around x. So it would give me so this term will cancel with this, but this has a positive sign. This negative cancel each other. So this again has a positive sign. So the leading order term would be so this dx by 2 added with dx by 2 will give me dx. So the contribution to the surface integral from the two x faces is this. Similarly, so if I look at the y faces, the the normal to the surfaces are in the y direction. So therefore, when I take the dot product with v, it is the y component which will make a contribution, which is expected. That outflow, so this represents outflow of mass. Outflow of mass is because of velocity perpendicular to that surface. So from these faces, it will be because of vy. So then in a similar manner, this will give me So the Taylor series expansion gives me the dy. The Taylor series expansion gives me the dy, and the area here is dx into dz. But if you notice, what comes from the area element and what comes from the Taylor expansion ultimately gives you the same factor, that ultimately this derivative is multiplied by dx dy dz. So the order and the logic behind why each of these contributions come in may differ. So here the dy dz came from the area, this from the Taylor series. Here this came from the area, this came from the Taylor series. But ultimately, in both cases, we get dx dy dz. So similarly, from the z faces would be so this was our equation expressing conservation of mass. So this had the derivative over the integral, derivative of the integral over the control volume, and integral over the control surface. So the derivative of the integral over the control volume, if it is an infinitesimal element, gives me this. So that gave me del rho by del t dx dy dz plus the surface integral. So this is the surface integral. So that gives me now this has to be equal to 0 for conservation of mass. Now all the terms are multiplied by this same factor dx dy dz, and dx dy dz is non-zero, so therefore I can cancel that factor, common factor, and write so this is the continuity equation. So if this equation is, so if a velocity and density field satisfies this equation, then mass is conserved. Now these three terms, if you look at them, then you'll notice that this can be written in a compact vector form. We know Now we know a scalar into a vector is a vector. So if I consider the product rho into the scalar rho into the vector v, that is a vector quantity, and its xyz components would be rho vx, rho vy, rho vz. So then these three terms together can be written as so this is the same equation. This I wrote out explicitly in Cartesian coordinate system in terms of components. If I write it in a more compact form in a vector notation, this is what it will be. Now, we can write it in an alternative form. If I expand out the derivatives, it is this derivative into this, which I can write it rearranging as Vx del rho by del x. Similarly, so I've taken this term, I've taken this, this, and this. I'm left with these three terms. So all of them have this common factor rho into now this again you can see can be written in compact vector form. Gradient of rho has x and y, x, y, and z components as del rho by del x, del rho by del y, and del rho by del z. So when you take the dot product of that with v, it would give you this. So this is this. And this you can readily see is del dot v equal to 0. The reason why we did this is that these two terms together have a certain meaning. Now, in an Eulerian description, rho if rho is specified in an Eulerian description, then if I take the partial derivative of rho with respect to t, if I take the partial derivative of rho with respect to t, it tells me how does rho vary with time if I take my measurement at a certain fixed point in space. So now if I'm interested alternatively in knowing how does rho vary with time, if I carry out my measurements not at a fixed point, but allow my point of measurement to move with the flow. So what is the, in a sense, what is the Lagrangian derivative? So there's a term used for it, the substantial or material derivative. So if I follow the material or if I follow the substance, how does a certain property vary? So rho is specified in the Eulerian description. Now if I ask, what is the rate at which rho changes as I follow the material? So to distinguish that derivative from the partial derivative with respect to time, we denote that as d rho by dt, capital D. This is the convention used for material derivative. So then, if I follow the material, then as time changes, not only does this t change, the position also changes. So the rate of change of rho as I follow the material would be so as I increase time, my x changes. So then the rate of change of rho with respect to time because of change in x would be the rate of change of rho with respect to x into the rate of change of x with respect to time. Similarly for now, since I'm following the material, the rate of change of x with respect to time must be the velocity at that point. So then, and this can be written in compact form as so now if I look at the continuity equation in this form, these two terms together represent the material derivative of rho. So I can write this as d rho by dt plus rho del dot v equal to 0.
Sir?
Yes.
Sir, can you please again explain the last step?
Last step means which?
Yes, sir. Yes, sir.
This step.
Yes, sir.
Okay. Expanding out the derivatives, we had shown that the continuity equation can be written in this form. So this part is clear, I think.
Yes, sir.
Then we showed that if we follow the material, then the rate of change of rho given in this Eulerian description, if I follow the material, then that rate of change following the material would be given by this. So then the d rho by dt is del rho by del t plus v dot grad rho. So the material derivative is, so how does rho change as I follow the material? So one contribution comes from the rate of change, the local change, and the other comes because my point of measurement is moving. So therefore the d rho by dt is equal to this. Is this part okay?
Yes, sir. So like we equate this both, right? D
So
means capital D rho by dt and upper expression.
So it means the d rho by dt is equal to this. So I had this here. So I can put in d rho by dt in place of this.
Okay.
So then this is what it is. Now, first thing is, if I have an incompressible flow, rho does not change. In that case, d rho by dt is 0, rho is non-zero. So then I get del dot v is equal to 0. So this is the condition of incompressibility. So if I have an incompressible flow, then the flow field must satisfy this condition that its divergence should be equal to 0. Now, what is the interpretation if I don't have rho equal to constant? So let me rearrange. Okay, so let me look at this equation again. The rate of change of density is equal to minus divergence of V. So then what does divergence of V mean? Del dot V dV is equal to this is from the divergence theorem, or Gauss's theorem, or Ostogradsky theorem. So that says del dot V over the volume should be equal to V dot dA over the entire closed boundary of the volume. Now, if I consider an infinitesimal volume, if I say my volume is infinitesimally small, then this I can approximate as del dot V into V. Now, V dt dot dA is the rate at which the volume is expanding, because dA is the surface area and V dt is the distance by which the area moves out. So if I'm considering a material surface, then this is the rate at which volume is increasing. So as I follow the so if my dV is a material element, in that case V dot dA is dV by dt. So what it says is, if I have a volume element V and I have a velocity which is everywhere outward normal, in that case V dot dA is a positive quantity, which means from the divergence theorem del dot V must be a positive quantity. So if del dot V is a positive quantity, the velocity diverges out from any point. So if it diverges out, then the volume must be increasing. So this is what this represents. The del dot V is the rate, fractional rate of increase of V. So it is the rate of change of V divided by V, the fractional rate of increase of V. So if I have divergence of V positive, it means my material volume. So if I have an Eulerian velocity field which has positive divergence, so positive divergence. So if I have Vx like this, then the del Vx by del x would be a positive quantity. And then I have velocity diverging out, which means my volume of a material element is increasing with time. So a positive divergence velocity field means volume is increasing with time. So if I now look at this equation, d rho by dt plus rho del dot V, if I multiply, so I had d rho by dt plus rho del dot V is equal to 0. If I multiply this by V, it would give me V del dot V, we found is the rate of change of volume. Which is a simply conservation of mass. That if I follow a material element, the rate of change of its density into its volume must remain. So the rate of change of that must be 0. So the density into the volume remains same. So what it says is, if I have a field with a positive divergence, that means its volume is increasing. So correspondingly, if I follow the material element, where if I bring this to this side, it will be a negative quantity. So rho must decrease. So if volume is increasing, the density must decrease in order to conserve mass. So that is what this represents physically. So this was in Cartesian coordinate system. We still need to see what form this equation will take if we go to some other coordinate system, for example, cylindrical coordinate system. So that is what we'll take up in the next class, because cylindrical coordinate system is something which is very commonly used in engineering. Now time is over, so if you have any questions, you can ask. I'll just take attendance.
So could you just go down? I have to note down the
Fun?
final equation. So
Uh,
the last step alone, I have to note down the equation, sir.
oh,
Sir, when will we have our next class test?
at the moment, I've still left it a little uncertain. According to the academic calendar, it should be in first week of October. So the two options are either to have it in first week of October or to have it just after the autumn break. So at the moment, I still haven't decided because there are a lot of uncertainties.
Okay, sir.
So depending on how much progress we make, if there are no interruptions and we make satisfactory progress, then we might have it before as scheduled. So if it is in first week of October, once again, maybe I'll take it on a Friday.
Thank you, sir.
So let's close here.